Welcome to Brain Vision.
Okay, in this problem we are given electrons and protons with wavelength of 0.06 nanometers, and we're asked to find for both what voltage would be required to accelerate these particles up to a speed in which their wavelength is equal 0.06 nanometers. So the equations we'll need the definition of a de Broglie wavelength, which is the Planck constant h over the momentum of the particle. We need to remember the definition of momentum, P equals mv, of course. And for the case of particles being accelerated through a potential difference, we can note that the particle starts from rest, and so its kinetic energy will be equal to the potential energy gained through this potential difference, which is simply the charge, E, times the voltage, the delta V. Note this is not electron volts, this is the electron charge times the voltage. And the reason we're using E for the electron charge is because it works for both electrons and protons. They have the same charge. Okay, so let's jump into it. So to start off, we can say lambda equals h over p, which is equivalent to h over mv. So we need to find a velocity of these particles being accelerated through a potential difference by noting that the kinetic energy will be the same as the potential that it gains, which is the charge times the electric potential difference. We can then say that since k is simply 1/2 mv squared, set that equal to electron charge times potential difference, and solve for the velocity. We are left with v equals root 2 ev over m. Which we can plug into our expression. And we are left with lambda equals h over root 2m ev. So this is the expression we will be using. We can simply plug in our numbers at this point. Or rather, we can solve for v at this point. So this is equivalent. If we isolated the voltage v, we would get v equals h squared over 2 m e lambda squared. And this is the expression that we will finally need to use. So the only difference for parts A and B is that the mass changes. So let's do it once for an electron. So for part A, we would have V equals 6.626 times 10 to the negative 34 joules seconds over 2 mass of an electron to 10 to the negative 31 kilograms. Electron charge, 1.6 times 10 to the negative 19 coulombs. And of course, our lambda of 0.06 nanometers. So this is 0.06 e negative 9. Almost running out of space. So plugging this all in and computing, we would have a V equal to 418 volts for part A. For part B, simply using the proton mass instead of the electron mass, we would have a voltage of 0.228 volts. So you see, it takes less of a voltage to accelerate the proton than the electron. And that's because the increased mass results in the lambda being intrinsically smaller for a particle with larger mass. Okay, thank you very much.